Mr. Moore's math class! Good afternoon, guys, and welcome to Mr. Moore's online classroom. Alright, like always, we've got plenty to get through today, so remember to grab yourself a piece of paper and a pen and a hot chocolate, put your feet up on the couch, and let's get stuck straight into the lesson. Hey! Alright guys, we're going to be covering a topic called differentiation using first principles today. Now, in order to do that, we need to revisit some concepts quickly that we covered back when we were working with rates of change. So let's have a look.
Okay, so if you can remember back to when we were doing our unit on rates of change, we came across a question that talked about a penguin needing a gradient of negative 0.3 to slide down on its belly. Now, we went about finding that gradient by substituting in two x coordinates that were close to each other to find the y coordinates, and then using those two to find the gradient between the 2 points. Alright, so what we used was x equals 4 and x equals 3 to help us out with this equation, and eventually we found out that the gradient between these 2 points was equal to negative 0.28. This meant that according to our calculations, at a displacement of 4 meters from the tip of the iceberg, the gradient of the iceberg was not steep enough for the penguin to slide down on its stomach. This was of course until Jerry piped in with a great idea.
But Tom, we can get 2 points that are closer together.
That's right, Jerry came up with the idea of using the value x equals 4 and another point that was closer to x equals 4, say 3.5, in order to find the gradient between those 2 points. What we found is that we ended up getting a gradient that was negative 0.3. This in fact actually demonstrated that the penguin could slide down on its stomach at a displacement of 4 meters because we found out the gradient was equal to negative 0.3 and it was much more accurate using 2 points that were closer together. But Jerry still wasn't happy with this value for the gradient, believing that we could get an even more accurate reading by finding 2 points that were even closer together.
But Tom, we can still get closer.
And he was in fact right. By finding the point at x equals 3.99 and x equals 4, we used 2 points that were extremely close together and we got an even more accurate reading of the gradient. So, what we found was the closer we got the 2 points together, the more accurate our gradient was for a given point. Alright, so the question that's being asked at the moment is the graph at top right has the equation y equals x squared minus 2x, hence find the gradient of the tangent to the curve at x equals 3. So what we're looking for is how steep this point here is at x equals 3, that is how steep the tangent is right there. Okay, so what we need to do to find that is use the point we're actually looking for, so x equals 3. And we need to use another point that's extremely close to it because the closer we get, the more accurate the gradient is. So let's use x equals 3.01, or in other words, 3 plus a little bit. Okay, substituting into the formula now, you get f of x is equal to x squared minus 2x. And substituting in 3 now, you get f of 3 is equal to 3 squared minus 2 times 3, which is equal to 9 minus 6, which gets you an answer of 3. So you get the coordinates 3, 3. Okay, substituting x equals 3.01 now, so once again write the formula, f of x is equal to x squared minus 2x. Alright, and substituting in 3.01, so f of 3.01 is equal to 3.01 squared minus 2 3.01, and that ends up getting us an answer of 3.0401. So you end up getting the coordinates 3.01, comma 3.0401. Alright, now you're substituting that into the formula for the gradient, so you have m is equal to y2 minus y1 over x2 minus x1. Alright, we need to go through and label our points, so you've got x1, y1, x2, y2, and let's substitute it in now, so you got y2 being 3.0401 minus y1 being 3 over x2 being 3.01 minus x1 being 3 gets you an answer of 3.0401 minus 3 is 0.0401 over 3.01 minus 3 is 0.01. That ends up getting us an answer of 4.01. Therefore, the gradient at x equals 3 is 4.01.
Now, to understand differentiation using first principles, we're going to have a look at something that I refer to as the ant's testicle theorem. Yeah, that's right, you heard me, the ant's testicle theorem.
Ding ding! Now our goal today is to be able to find the gradient of any given function for any given point p. Now this point P will have an x-coordinate of x, and to find the y-coordinate I would substitute x into f of x, which will give me the result f of x. Therefore, with an x-coordinate of x and a y-coordinate of f of x, the coordinates of P are x, f of x. Now, to find the gradient at the given point P, I need to have 2 points. Therefore, I'm going to introduce the point Q. Now, Q has an x-coordinate of x plus h, where h is the horizontal distance between the x-coordinates of P and Q. And of course, the value of h can get smaller as the coordinates get closer together, or larger as the coordinates move further apart. For the most accurate results, we want h to be equal to a little bit. Now, if we substitute in x plus h into f of x, we end up getting a y value which is equal to f of x plus h. Therefore, the coordinates of Q are x plus h, f of x plus h. Now that we have our 2 points, we can find the gradient of the chord that connects these two values. But to find the gradient of the tangent at the point P, we need to move the point Q in much closer. This will make the h value extremely small. The smaller the h value is, the more accurate our reading is for the tangent at the point P. Therefore, we want to make the value of h about the size of an ant's testicle. Watch what happens to the green tangent line and the size of h as Q moves closer to P. And why stop there when we can move Q closer, making h smaller? Now that we've made the value of h about the size of an ant's testicle, have a look at how much more accurate the green tangent line is for point P. However, of course, the closer we get the 2 points together, the more accurate the green tangent line becomes. Now, if you have a look up the top left-hand corner of the screen, I'm going to introduce you to the formula that we use when differentiating using first principles. So let's take the point P, with the x-coordinate of x and the y-coordinate of f of x, and the point Q, with the x-coordinate of x plus h, or in other words, x plus a little bit, and the y-coordinate of f of x plus h. Now to find the gradient, we substitute these 2 points into the formula m is equal to y2 minus y1 over x2 minus x1, labelling the point P x1, y1, and the point Q x2, y2. Substituting in now, m is equal to y2 being f of x plus h minus y1 being f of x over x2 being x plus h minus x1 being x. Now on the denominator, the x and the negative x actually cancel each other out, leaving us with the gradient formula m is equal to f of x plus h minus f of x over h. So what we've essentially found is the formula for differentiating using first principles, where we call the gradient function f dashed of x, where this is equal to the limit as h approaches 0 for f of x plus h minus f of x over h, and because we can't divide by 0, our denominator h cannot be equal to 0. If we think about it logically for a second, h needs to be equal to a little bit. If h is equal to 0, the points P and Q will be at exactly the same location, making them the same point, which means we're back down to only having 1 point, and of course we need 2 points to find the gradient for a function.
Wow! Can the ant's testicle theorem maybe even help us out when coming up with a gradient function that represents the original function? Well, let's have a look.
Alright, so now we're going to differentiate y equals x squared minus 2x using first principles. Now before what we did is we found the gradient at the point x equals 3. Now to do that, what we did was we substituted in x equals 3, and we got an answer of 3. And then we also substituted in the point x equals 3.01, and we got an answer of 3.0401. Right, well let's have a look at this. In general terms, so rather than doing it at a certain point, we're now going to look at it in general terms. What this means is we are substituting in x, and we'll get an answer of y, or in other words, f of x. Okay, so for this one, we're going to substitute in x plus an ant's testicle, x plus h, something so small that you can't see it. And when you substitute in x plus h, you're going to get in f of x plus h as an answer. Okay, so what's this mean in general terms? Well, we're going to substitute into the equation f of x is equal to x squared minus 2x. First of all, for our first point, we're going to substitute in x. So you get f of x is going to be equal to x squared minus 2x. Okay, so that hasn't actually changed. So you end up getting the coordinates x and x squared minus 2x. That's our first point. Our second point, though, is going to be a little bit different, because we're going to do f of x is equal to x squared minus 2x. Alright, we're now going to substitute in x plus h. You get f of x plus h is equal to x plus h squared minus 2 x plus h. So instead of substituting x for the second point, we're actually substituting x for something that small. It could be about the size of an ant's testicle. So what we've got is f of x plus h is equal to x plus h squared minus 2 x plus h, because instead of writing x, we write x plus h for every value of x. Okay, let's go through and simplify that. So f of x plus h is equal to x plus h times by x plus h minus 2 x plus h. That ends up getting us x squared plus 2xh plus h squared minus 2x minus 2h. So therefore our coordinate at this point is equal to x plus h, comma, x squared plus 2xh plus h squared minus 2x minus 2h. Okay, I know it's a long coordinate, but let's substitute it into the equation for the gradient. So m is equal to y2 minus y1 over x2 minus x1. Okay, so let's label our coordinates x1, y1 and x2, y2. And what we're actually finding here is a function for the gradient. So what we actually call it, instead of m now, we call it f dashed of x, and that will be equal to y2 being x squared plus 2xh plus h squared minus 2x minus 2h minus y1, which is x squared minus 2x in brackets because we're minusing the whole part of it, over x2, x plus h, minus x1, which is x. Alright, so let's just take this out of the brackets to start off with. So you get x squared plus 2xh plus h squared minus 2x minus 2h minus x squared plus 2x over, we can simplify this. You've got an x and a minus x, so they're going to cancel each other out, so you just get h. So then what we're going to do is we're going to simplify the numerator. So you've got an x squared here and a minus x squared, so they cancel out. You've also got a negative 2x and a positive 2x, so they cancel out. So you end up with 2xh plus h squared minus 2h on the top over h. Now, these h's can come out as a common factor because they're all in there. So you end up with h bracket 2x plus h minus 2 over h. Therefore, f dashed of x equals, with a lim approaches 0, because of course h cannot equal 0 on the bottom here, because if it does, it doesn't exist. So that's why the limit of h approaches 0. That will be equal to 2x plus h minus 2. Okay, and as the limit of h approaches 0, we just substitute in h equals 0 for here. So you end up with f dash of x is the limit of h approaches 0 is equal to 2x minus 2. Therefore, f dashed of x is equal to 2x minus 2. So this here is the gradient function for this graph. What that means is if I substitute in any value for x, so maybe 2, 3, 4 or whatever, it'll actually tell me the gradient of the curve at that very point. I no longer need to find 2 points. So for example, if I wanted to find out the gradient at the point x equals 3 like we did before, what I can just do is substitute in 3 into the gradient function. So you get f dashed of 3 is equal to 2 bracket 3 minus 2, which is equal to 6 minus 2, which we end up getting an answer of 4. Now if you remember back to what we did in the last worked example, what we got was an answer of m is equal to 4.01. Now the reason we got 4.01 is because we obviously didn't get close enough to the 0.3. Alright, so that means we've got this tiny little error of 0.01. If we had have got a little bit closer, say 4.00001, our answer would have looked closer and closer to 4. This here gives us our exact value of the gradient at x equals 3.